let me. Well, good afternoon, everyone. Hopefully you can hear me. I can get a thumbs up from someone, or someone in the audience could respond. That's one of the
We can
participants.
hear, yeah, we can hear you very well.
Okay, very good. Okay, thank you. Thumbs up. I got many thumbs up. Well, my name's James Rickles. I'm the director of the Lehigh, or let me say the official NHERI Lehigh experimental facility. Today, we're going to have a virtual workshop that is entitled Capabilities, Project Examples, and Guidelines for Proposals. And before we start, let me just indicate what our goals are. We're looking to disseminate information on the use of our facility to conduct state-of-the-art research and also use recent advances in simulation. And the objective is to mitigate the effects of natural hazards on the civil infrastructure. Also, we're going to showcase some experiments and simulations, but utilize different aspects of our facility, including component tests, hybrid simulations, and large-scale test beds. And this is to illustrate to potential or prospective researchers how you can utilize our facility. Our other objective is to identify and develop opportunities for the audience, for researchers to utilize our facility. And what we're hoping is, as a follow-up, that you'll submit proposals to use the facility. Now, we're going to have presentations by several different members of the staff, including myself, but I'm going to hand the podium over to Dr. Joe Saunders, who's the operations manager, and then he'll introduce the rest of the staff and the agenda. Okay, so with that, Joe, I'm going to hand it over to you.
Thanks, Jim. Let me just get these up here and I'll share my screen. Please hold. Can you see those slides, Jim?
Yes.
Okay, perfect.
Mm-hmm.
All right, great. So as Dr. Rickles had mentioned, my name is Dr. Joseph Saunders. I am the NHERI Lehigh Experimental Facility Operations Manager. I'm going to just briefly introduce you to the team here at NHERI Lehigh, go over the agenda, what we plan to present here, and then follow up on what Dr. Rickles had mentioned already on what are our objectives. So first, the team here, the team is what makes NHERI Lehigh happen. Everyone you see here, and then we have additional staff to really make this organization great and help provide you capabilities and research opportunities. So to start, Dr. James Rickles and Dr. Richard Sauce as PIs and co-PIs. They have been our leaders here at NHERI Lehigh for over 20 years. So a vast amount of experience leading the charge. As I had mentioned already, I'm Dr. Joe Saunders, the operations manager here. We'll hear from Dr. Leon Cao. He's a research scientist who has been here for 6 years now. He's got a good amount of experience doing hybrid simulations, and he'll present to you a lot of work that we've done here and he has done here. We have Tommy Morello, who's also online. He's our IT systems manager. Derek Fritchman, our Atlas lab manager, who you will not hear from, but he is integral into making all the things happen here. And Sandra Nemeth is our financial manager who oversees our finances. So briefly, the agenda today, I've got Dr. Rickles with the welcome, myself just briefly going over the agenda and our objectives, and then Dr. Rickles will go over the NHERI science plan, and then an overview of our facility and how our facility really does a lot of work that supports the NSF science plan, the NHERI and NSF science plan. So hopefully after you see that presentation, you'll have some ideas of how you can, um, work with our facility with a plan that coincides with the NSF science plan. Then Dr. Rickles will go through our facility in large part a description and details of our facilities, what resources we have available, how we can help you perform the research that you want to do here. Then Dr. Cow will present many of the projects that we worked on. We worked on a lot. He's only going to show a select number, but we have worked on many over the 20 years that we've been in operations. And then I will finish our workshop here today with some guidelines on what you need when you're putting either a proposal together, or you have a proposal already, but you think you might want to do some work here. What are the things that you want to be thinking about, and what items you'll want to bring to us in order to help us help you facilitate your research. And then finally, we'll open up the discussion for any questions or comments, or really anything that you have questions about, and how to use the facility, how to if you have ideas, if you'd like, we can set up meetings to further discuss research proposals or projects that you want to do. So that time is committed to having an open conversation. So as Dr. Rickles had mentioned already, our objectives here are to disseminate that information about the facility itself. So we want you to understand what we offer here at NHERI Lehigh and how it fits into the NSF science plan. Then we want to showcase some experiments and simulations that we've done here. So you might have some ideas about what we do already, but seeing examples are always really helpful to understand what the capabilities here are at NHERI Lehigh and how we can support the research that you want to do. That's the name of the game. And then finally, as I had mentioned in the previous slide, right, we want to have an open conversation if possible, if you're interested, to develop opportunities for you to use the facility. We have, I think, really world-class facility here, and incredible experimental and simulation capabilities. So we'd really love to have researchers use our facility and do great research. So with that, I think I've got Jim, you're up next with the science plan and the overview of NHERI Lehigh. Jim, you're muted if you're
To
talking.
make sure you unmute.
Things
Just
not
some good
sync.
old Zoom technical
We
difficulties.
can hear you now.
Well, Zoom's a pain in the butt. They need to have some competition. Okay, hear me and see the slides okay?
No slides yet.
No slides. We
Okay.
see you and hear you.
Again. Okay now?
Perfect.
Okay. My theory is there's incompatibilities between Microsoft and Zoom. I think they're competitors, but we won't talk about that today. Anyway, so welcome back. And what I'd like to do now is to continue with the science plan and overview. There's quite a bit of information, so I know you won't absorb it all, but try to dwell it really on the highlights. And so all the sites are required to have a science plan. Our science plan is stated as being one in which we provide to the community a next generation multi-user facility to conduct transformative research. And in doing so, we look to integrate very carefully, but also logistically, numerical simulations of experiments. So that's cyber physical, another way of saying that. And the goal is to use it as a tool, not as a novelty, as a tool to advance natural hazards engineering, research, and education. And the whole goal is to face the challenge of community resilience. So that's really our plan. And what it allows you to do is to meet a few objectives. One of the objectives or challenges is to develop and improve concepts for renewal and retrofit of the built environment. So if you're writing a proposal, you want to think about some of these aspects here. Exploitation, new emerging materials, there's many new materials, including like metamaterials that are evolving. Development of new concepts that are resilient and economical as well. If they're not, then it's not going to be very feasible. And very, very important there, because what the National Science Foundation likes to see, and really you got to think about this, you can't test everything. You can't test everything forever. So our goal here is to do high quality experiments that you can acquire some very detailed, refined data that you could develop, or someone else could follow up and develop accurate physics-based computational models that these are then used for numerical simulations as follow-up. So that would be the next step. Now, a few other things here. We focus on large-scale multi-direction. And I have real-time hybrid simulations underlined, but that's not the only thing we do. And you'll see this as part of the examples that Dr. Leanne Cowell will show. But hybrid simulations, it's, again, cyber physical. It combines experiments that are physical with computer-based simulations, and they're linked, right? They're acting and they're synced together. And it's to evaluate then the performance of the system. It's not really just the components, but of the system. You can see something in the lower right. That's just sort of an example I'll show some more later. Now, the other thing is sometimes we get researchers are a little bit overwhelmed at first about using our facility, or it's a little bit daunting to write a proposal. And what I'd like to do is try to comfort you in saying that we have been doing this for a while. We try to always adapt towards evolving opportunities and techniques. But in doing so, we develop user-friendly tools. So that allows you as a researcher to readily utilize our facility to do some high-end experiments and use the algorithms to perform the research that you need. Now, just to give you some examples further here about what you can readily perform, I think we've done over 6,000 probably real-time hybrid simulation. I think the record is 403 days, but in any event, real time is real time. So 40-second event or 5-minute windstorm, that's how long the experiment takes. And we could readily do those in 3D. And we've built things from the ground up. We don't bank on using commercial software or taking software that's open source and trying to mold ourselves into that software. It doesn't work. So we've built things from the ground up, but in doing so, we can create some pretty sophisticated, complex nonlinear modeling that includes both geometric and material. And as a result, you get some robust computational models. The outcome of that is you could then be able to assess numerous response modification devices, say that are rate dependent and are in systems that are 3D and multi-natural hazard. What does that mean? Well, not everything is an earthquake, right? That's historically what initially NHERI was all about. But we have storm surge, we have, flooding, tsunami. That's all what we have in mind here when we talk about multi-hazard. And I think what's very important here is, anyone can do an experiment if they have the lab, but what's very important is the accuracy, because if it's not accurate, then the data doesn't maybe make sense and you won't be able to really be able to discern what's going on and maybe publish it. So we try to incorporate our knowledge and our expertise into producing accurate experimental results in 3D. And this involves a number of things such as nonlinear kinematics, in addition to actuator dynamics and nonlinear modeling. So we have that experience with those aspects. And I already mentioned the precise action control. That's very, very important, very important. So what are some of the impacts here? And this is something you want to think about when you write a proposal. You know, you have an idea, but you got to express to the reviewers and the National Science Foundation or the sponsoring agency is what is the broader impacts? Because this will separate you from the group of other people submitting proposals. So here are some impacts about our facility, and we can address key questions through the research that could be formed that could lead to, you know, various results. One being the development and implementation into practice, new natural hazard mitigation strategies and innovative structural systems. We have a lot of the staff, including myself, that are professional registered engineers, so we have a really good sense what goes on in the real world. And a number of us have also worked. Most all the staff has worked in practice, so we brought that to the facility for you. The other broader impact is enhancing the understanding of the response. This is in the NHERI science plan. This is one of the things that is emphasized here. And what I add to that is accounting for soil structure interaction as well as fluid structure interaction effects. You know, we've managed to do that. The other thing is a comprehensive, not comprehension, but a comprehensive system level effects on the structural, non-structural components through this 3D hybrid simulation. You know, components don't act individually. They're in the structure, there's a system, and you have to account for those interaction effects. It's very important. I already mentioned the fact of high quality data. This is going to lead again to more improved models for response prediction. Now, what's also very important, and this is something that funding agencies look for, is the workforce development. So we've got a huge education community outreach program, which we take pride in training the next generation of the workforce. This will be your PhD, your master's degree students, and your undergraduates, and even in high school and other grade schools, to try to encourage them to get into science and make a contribution and train them. Now, here are just some examples. I'm going to be rather brief here, but these are some example projects. Some of them are real, others are what I could envision here. We can look at semi-active control devices that are autonomous to enhance the resiliency and performance against multi-hazards. This approach would be real-time hybrid simulation. We could look at advanced bracing system and shape memory alloys. We actually have a project already in the lab on that someone followed up on. The approach we would take, and you'll see a discussion later about the technique. It's called quasi-static or hybrid simulation. There's interest in developing, as I say, complex computational models. Well, you need the data. So here's an example in which the facility could be used to look at advancing multi-directional, through multi-axis loading of reinforced concrete materials here. There's non-structural, there's a floor isolation systems that sometimes the contents of buildings are more valuable, both financially and also just the impact it has on the building itself. So here's a project actually is ongoing from the University of Oklahoma that's related to multifunctional floor isolation systems. We also have additional non-structural components for minimizing hazard losses. This could be cladding or other things that's added that also dissipates energy. Soil structure interactions becoming very important. It could help, it could also hurt you. It could hurt you if you ignore it, and it adds flexibility, and it could help you if it adds radiation damping. So you need to really account for it, particularly in tall buildings where a soft soil with that heavy load on it could have an effect. Semi-active controlled cladding, I mentioned cladding. You can have semi-active controlled cladding that we've worked with. Transportation systems. NSF does allow you to now look at transportation systems, and as you know, they're really the arteries of the U.S. economy here to transport things. So this is very important. Fire, fire hazards is also now fair game with NSF. I'll give you a reference here in a little bit later. We do have a furnace that we can use for that purpose. Coming back again to soil structure interaction, you could have response modification devices, but guess what? Especially with TMBs, it may not be tuned properly because the soil that's actually there in the system you admit it in the model, and we could account for that in our simulation. So it's very important to consider the system as a whole, including all these other effects. And very, very important, and people have come to realize this more recently, of all the storms and the climate change, is the coastal infrastructure and the inundation from storms or tsunamis. And we have, new faculty member, Claudia Reich, who's an expert in this area that could lend some guidance on that. She's doing research as well herself in this topic. So with that, let me describe to you the facility. We are originally a NEE facility, Network for Earthquake Engineering Simulation. But we really like to think of ourselves as being a real-time multi-directional facility. And earthquake you can replace with multi-hazard if you wish, but earthquake is where we initially were born. My own background is originally earthquake engineering, but obviously I had to migrate towards other areas in order to adapt towards the pressing needs in research. So we're very unique in that we have a portfolio of equipment and instrumentation and the infrastructure itself. You see the lab floor there before we moved all the test specimens, et cetera, in. That's part of the infrastructure that which we have test beds, and we use that with simulation control protocol that we developed ourselves. And I should mention some of these that we developed now have been ingested into MTS's control software. So they've taken what we've published. So we just want to add, we have some credibility there. And the goal is large scale and multi-direction. And multi-direction does matter in hazard mitigation, and large scale does too. Now, on the right, you can see many experiments going on. I think I counted 8 here. We currently have 13 in our lab, but we manage. Joe Saunders has a big stick and he makes sure that things get pushed in the right direction in the lab, but we're very efficient in that we can conduct concurrent multiple large scale experiments. So the wait time is not like a shake table where you have to wait till someone gets off. We allocate space basically based on the need and the demand. Very experienced staff. I mean, they could do anything. Some of them have been around for 40 years, longer than I have here at Lehigh. Now, I want to mention the Atlas Center. So our facility exists within the Atlas Center, which originally was conceived as an NSF Center for Advanced Technology, Large Structural Systems. So we built upon that know-how and used that facility. So we exist within that. And what it does is it provides us with also additional resources and, of course, the infrastructure. So the reaction wall, the strong floor, all that stuff is really the Atlas infrastructure that we added on to. So it gives us a lot of leverage. Here's the outside of the building. When you come to visit us, we're going to have an in-person researchers workshop. I think in November. Hopefully you'll come. You'll enter here through the front door.
Very good. Come on, get out. Watch your head when you get out. Do not bump your head.
Okay, I think we're okay. So just to kind of a little bit about our expertise, and we, as I said, we're pretty diverse in our faculty and also our research engineers and staff. So we have expertise. My own background, structural engineering, but I do earthquake engineering as well. I've done some wind, but we have other experts in that. Geotechnical engineering is Professor Mohammed Suleiman. He's our faculty, and he's actually the co-director of the Atlas facility. We have expertise aeroelasticity, wind engineering, fluid and hydrodynamics, probabilistic-based modeling. We have a catastrophe modeling center that's directed by Professor Boccini. Structural monitoring and damage assessment have expertise in that. That's expertise lends itself towards Professor Shirming Paksad. And coastal structures, the inundation from storm surge. Unfortunately, I don't have all the names here, but hopefully you can ask again later. That's Professor Reich. She's a new faculty member that's been with us since beginning of the year. Now, I like to think of ourselves as being pioneers. We didn't invent real-time ambient simulation, but I like to kind of think we've taken it to the next level. What we've done, and myself being a structural engineer by trade and having worked in industry before I came back and finished my academic training, I knew how to design structures. I understood how engineers face challenges. And the reason I got so interested in hybrid simulation before I took it to real time is to develop it as a tool, not as a knowledge, say we've done this and then you apply it to very simple academic problems. Our goal is to apply it to real problems that you can get an answer for a real structure and have meaning. So keep that in mind. Now, on paper, I don't want to simplify, but it's not conceptually difficult, but it's the know-how that's important. That's how our lab is actually gained that knowledge, all the way from the IT through tightening the nuts and the bolts, you know, especially at large scale experimentation. Now, the other thing is we have a very strong relationship with industry, you know, practicing engineers, and we're familiar and participate, in fact, in a lot of the codes and standards. So we have good knowledge about how, in the end, your research will make a difference and how to get it transferred to the right place. And I mentioned the staff, very experienced. As I said, we have a few staff have been there about 40 years. Now, let me go through some of the protocols and the resources. And maybe some of you know, but I should maybe explain. I'll just be somewhat brief, not really any technical equations to show, just concepts here about hybrid simulation. So let's look at real time, and let's consider as an example for multi-natural hazards, we'll consider wind and earthquake here. We have this tall building, let's say 40 stories, and you've been asked to assess the effects of this building during its lifetime. So you're in a situation which you say there's wind, you know, tall buildings usually controlled by wind, but if this is situated, say, in a seismic zone, you'd be concerned about the seismic performance. So here I show this 40-story building under the wind loading, and you know, scale is important, and you say, well, I can analyze the whole thing numerically. So, well, let's see if we can just throw it into the computer. So we realize there's some nonlinear viscous dampers, and contrary to common thinking, nonlinear viscous dampers actually change characteristics depending on the event. So we're going to take that to heart and have to model those physically. So we can have that numerically model and have, say, confidence in the accuracy. But then what do? You can't put a 40-story building at large scale in your lab. I mean, if you can, you'd have the world's tallest lab. So we're going to have to accommodate the resources. And so here's just showing some wind tunnel. We've interacted a lot with FIU, Florida International University. And let's say we have some wind loading that we've conducted, some wind tunnel test. We're going to take this system and divide it into two domains, two substructures. What we can model with high degree of confidence, we're going to put in the analytical substructure. This is, say, a finite element model, or it could be a neural network. And what we can't model with confidence physically, we're going to put into the experimental substructure. In this case, just the dampers, but it may be more, but in this case, just the dampers. So that's in the laboratory. These two things are part of a system. They have to talk to each other. They have to interact. So we have a coordinator that ensures that. So for a given point in time, you have these equations of motion, inertia, the damping, that's the second term of the velocity on the left side. We have RA and R sub B, capital RA, R sub B. Those are restoring forces. That's the response of the analytical on the left side, response to command displacements, and the experimental R sub B is the response from command displacements to it. And the right-hand side is the applied load, which, let's take a point in time, I plus when we have the applied load. We integrate the equations of motion, we send command displacements to the two substructures, and we get back to restoring forces. Now, this has to be done well within the time step, because if it's not, you have delay. And you have delay, it's chaos. You're going to put energy in the system, and believe me, we've experienced this before. It's going to blow up on you. So this has to all be synchronized and has to be done well within the time step. So we use special integration schemes in order to achieve that. And if you're able to do that in real time, you have the response. Now, everything doesn't have to be in real time, so we can slow it down. Tommy Burler, IT expert, has could run things any pace you want. I guess even faster in real time if you had to, but that wouldn't really be necessary. Now, if you want to go a different event for this, the novelty here is that for earthquake, you can change the forcing function as shown here. Everything else essentially remains the same. Of course, the response will be different. If we had fluid structure interactions, the same thing, where if you want the interaction, we have been able to account for true fluid structure interaction, where based on the relative motion of the fluid and the structure, we can calculate the response. So I'm not going to present that today. I think Liang Cao will present some of that later. So why is this important? Well, it's in real time, it's simulation of the response in the hybrid sense. In hybrid, it's cyber plus physical. Cyber is well understood. You can model it numerically. You can have various experimental substructures you link with the cyber. And again, the physicals, you don't well understand it, so you need to model it physically, but you better have the right interface boundary conditions, which is something we understand fairly well, really well, should I say. So we set up the right experimental substructures for you, and we'll talk to you about what we could propose to make your experiment work. And we could accommodate large scale. Large scale is very, very, very important. Not everything is scale. When you get the fluid structure interaction, multi-physics, you cannot use reduced scale models. It doesn't work. And so it's very cost effective. We get the best of both worlds, numerical and physical. And again, you can incorporate a component into the system. This is why it's used as a tool. And you can look at rate dependency. So if you have the need to look at the system and you're going to look at rate dependency, real-time rapid simulation perhaps is the thing you want to consider. Now, just a few capabilities. So we can do large-scale real-time rapid simulation. You see this on the right. There's a yellow frame inside one of our bracing frames. The researchers are noted below here. We can also do large-scale hybrid simulation where we slow it down. Again, not everything's rate dependent. We can also, rather than model, you saw previously a lot of the physical structures, this is the yellow and white. We may have a real good model for that. So we may just have to have the dampers shown here, or 5 dampers across the bay, and actuators attached to each. Those dampers would say be located throughout the structure. This is multiple experimental substructures. Now, we have participated with various facilities in doing geographically distributed hybrid simulation, and we could work with some of our audience if they have the need, where you'd have, say, the experimental component in your lab, and we'd work via the internet, connecting the numerical part with the experimental through the coordinator. We've also done that actually in real time. I want to mention transportation momentarily. This was a transportation structure looked at with UIUC Lehigh. And there is this opportunity now. You can make a note about this. It's basically the ECI program where you can look at transportation systems here. It used to be off the menu, now it's back on. This is some other bridge work. This is Dr. Joe Saunders' level of expertise, so he can give you a lot of information on that. Orthotropic bridge tech, full scale. We've then geographically distributed real time. There is a latency in the internet that we have to deal with, that we've managed. This was done with Dr. Kim and Professor Richard Christian at UConn. And I want to say we just don't do real time, and we do a lot of characterization tests. This is predefined loader displacements. Here are just showing some examples on dampers, just trying to characterize the damper, maybe get the parameters to a model that you're comfortable with. And also we have new types of damper. These are rotary friction devices that have really very, very high efficiency. Not only on dampers, but also systems. This is a coupled shear wall, the lower 3 stories of an 8-story structure that we characterized for Dr. Karam, Professor Karam, and Mike McGinnis. They're from Notre Dame and UT Tyler. And this is also using digital image correlation systems here. Fire as well, we have a furnace. And again, you can go to the ECI program at NSF. You see that that's actually allowed. The person that has a lot of expertise in this, I've used this a little bit, but the person that really is the expert is Professor Spencer Queel. He's one of our faculty members here. Here's the link to that. And also non-structural dynamic testing, piping systems. You say, oh, well, big deal. But guess what? If your plumbing doesn't work in the building where there's a sprinkler system, the building is not allowed to be occupied. Doesn't matter if it's from an earthquake, if it's from an inundation or heavy windstorm. You have to have the non-structural components such as these functions. So we've done multi-directional dynamic testing to test the couplers and also the bracing, just dynamic testing here. I think Leanne Cal may or may not go through that. If you want, we can talk more about later. We have a shake table, multi-directions, and we can do real-time hybrid summation with the shake table, showing some results above for some bearings, working with Scott Harvey at University of Oklahoma. Tsunami debris, we have a ability to impact test. We'd have to reconfigure some things that have in the back, but we do have that experience. This is dynamic impact loading. And soil, we have various soil boxes. This is one of them. This is, there's three of them. This is the mid size. We have large, medium, and small. This is the medium size, 6 by 6 feet. We've done offshore wind turbine tests in real-time rapid simulation, accounting for soil structure, aeroelastic, hydrodynamic loading, and develop basically the models, the modeling that stuff ourselves, so it's not a black box. And so let me talk about the infrastructure. We may come back to that if you have questions. Here's some dimensional lab. And I'll just list it in pyramids. We have coming down towards us 100 feet of linear spacing or these tie-down points, which are 5 feet on center. Across the width, it's around 50, well, actually 40 feet, and the wall itself is 50 feet and steps down. Each of these points, we could tie down equipment or a specimen or actuator. So you can see the floor has the same thing, it's multi-directional. The hydraulics runs around the circumference. So we can access any point on that floor. This gives some dimensions I mentioned already, and it's unfortunately, if you're used to metric and pure units is what I listed, I think you can convert that in your own time. So this is part of the Atlas infrastructure. We actually outfitted that with some dynamic capabilities, and so we took advantage of the hydraulics supply system, added that, some other things I'll talk about later, but there's over 30 additional actuators that we have besides the ones we have for our NHERI, which I'll get to that in a little bit. Digital controllers, many acquisition systems, array of conventional sensors, but also advanced sensors, and we have equipment, auxiliary equipment to move things around. Example of 40, kip crane to position things in place. Now, that's the Atlas. That was the shell. We outfitted some pieces in the shell that was basically NHERI. Started this in 2002. Over the years, 22 years later, but it didn't take long to put it in. We did that all within 2 years, but we added hydraulic power. This is an accumulation system. We have already existing pumps. We have 6 pumps, perhaps 5 to 6 pumps. But actually 5 pumps, 120 GPM each. That's 600 GPM total. A distribution line to take the hydraulic power around the lab. Accumulation system allows us to go more than 4,000 gallons per minute. We can go over about 1.2 meters a second, and these actuators are shown below. These are large dynamic actuators. Now, what we've done is to look at demands, and so certainly we could accommodate earthquakes, very demanding earthquakes for 30 seconds. Earthquakes may be longer, but the demand won't be as high, but we can easily accommodate that, as well as other natural hazards, such as windstorms and inundation due to storms. Give you an idea, I already mentioned some things here about hydraulic supply system, that accumulation system. Dynamic actuators in imperial units shown here, but 517 is about close to 2,400 kilonewtons. And the other one is a little bit smaller here, 382 kips, but we have 5 of these. The stroke is plus or minus half a meter. We can go actually 1 meter, 500 millimeters. And here is the maximum velocities. We can actually go a little bit faster if you need, because we add more servo valves to the actuator. We have 10 of these we can reconfigure per actuator. Now, what are some of the projects? Again, I want to instill in the audience that we can handle multiple projects. We have very experienced staff. Joe is good at coordinating things. He's technical by nature, so he's done experiments himself, so he can relate to everything, and he's doing experiments. In fact, about to do more experiments himself. So be able to arrange things. Just some examples. We conduct these experiments concurrently where we have, active cladding test beds. We have something called the spine system with a special connector with the DIC set up on the right. That's Lee and Cal set that up. 3-directional mass timber test to look at shear walls that are self-centering. This is a prelude to the toll wood project that we were part of at San Diego. And then on the right side, ongoing experiment, Dr. Cal will talk about. This is a collector project, 2 million pounds of loads being applied to that specimen. So that's the only time you can't go in the lab when we do this test. It's for safety reasons, but we can do all these without much delay between the experiments. Do we do them all concurrently? No, because we don't want to run the risk of having a crosstalk, but we can go in the lab, do one in the morning, and when we're done with that, we change the controller over to using the equipment on another location in the lab. So we have an integrated control system at Tommy Marilla, our IT expert, set up. It's got various workstations that are configured with and linked with ScramNet, that's basically shared memory. What this allows us to do is to configure the system to do the tests that I showed you, but even more. If someone comes up with a new novel idea, we can entertain that. The algorithms we have, we can run in real time, or if you need, we could expand the timescale to slow it down, whatever the user has a need for. Now, distributed hybrid simulation, we have our own software, but we've also able to interface with OpenFresco. It allows us to interface with OpenSeas. If you ask, do we use OpenSeas for real-time hybrid simulation? The answer is no. Hybrid simulation, in our case, requires customized software because of the synchronization. OpenSeas is a good program, but it just doesn't suit our needs. Now, again, we're flexible that we can inject software and middleware packages developed by the users, but I warn you, it'll go an interrogation because we want to maintain the integrity and the safety of that. So we'll go through a number of tests, but we've worked with many users in that regards and come up with new novel software for testing. A few other resources, we have our own specimen preparation. This is in the front of the lab. You see a frame here that was built. Mechanical testing, we have resources to do mechanical testing. We have an auditorium for ECO activities here that we can provide an audience a nice place to hear our in-person researcher workshops. In addition to prep areas, we have other laboratories, intelligence structures, mechanical testing, welding, and joining materials and microscopy. And of course, offices. We have a lot of visitors and we accommodate them with offices. So students certainly should come, researchers. We've had students stay as long as a year. Not that it takes that long, but we accommodate you. And meeting rooms, of course, a lot of Zooms like today. Storage areas that we can store specimens, although we don't like to, store a lot of extra things that aren't needed. But we have storage, and it's a secure environment and a safe environment, both in diversity, inclusiveness, but also from a monetary perspective with the equipment. If you have any other questions, I'm sure you do. This is our website. I think it's hard to remember, perhaps. Just type Lehigh or NHERI Lehigh, and you'll eventually go to this link, and this is a front page. You'll see many different pull-down windows. This has, of course, been updated. We always have more news. There's a video here you can play, facility overview. You can go to various links. One of them is under resources. And I encourage you to visit this. If you're going to write a proposal, take advantage of these resources. These resources have evolved over our experience and our interaction with researchers writing proposals. For instance, we have the user's guide, questions for pre-proposal. There's a checklist for people writing proposals, equipment and facilities. This gives you information you'll need. Some of our test beds, and then our science plan, and various other things too you can actually use in your proposal. So with that, I guess the test beds, let me briefly mention test beds here. We have various test beds. One is a large lateral low resisting frame test bed that you see the dimensions here. We can put, they're really planar frames, but you can simulate those in multi-direction if need. We also have non-structural simulator. This is one in which we have piping that I showed earlier running throughout the floor of a building system. This is a multi-directional test. Multiple test beds for actuators. Each actuator is in a separate test bed, and each test bed has, say, a damper or device. You can use those for just characterization and real-time hybrid simulation. Some of the capacities of those test beds are really based on the actuator, so the fixturing is stronger than the actuator, so you can go up to these capabilities. The real-time hybrid simulation also is extended towards our cyber physical structural systems lab. We got an extra 4,000 square feet in which we've created this laboratory. We've actually expanded the footprint. It's used to enhance research issue and researcher training, so you could participate. It gives you a lot of hands-on experience. We also have researcher training workshops and planning workshops that you can go on our website and you can actually arrange for one to come and get trained and actually generate some pilot test data for a proposal using some of the test beds. So it's a little bit smaller scale, but not too small. Depending on what you're testing, it's actually full scale. But as I said, it's really low cost and hands-on and very easy to arrange and very efficient for that reason. These numbers don't mean anything, but I'll show you the capacities related to these model numbers here. We have both hydraulic and electric actuators, integrated control system. Then this system is identical to the twin, the sister, the big sister that originally we had in the main control room. They're identical in architecture and hardware. So if you arrange and do something here, you could transport it to the other control system as well. And the two systems can talk to each other. Here are some of the actuator capacities. Again, we can go pretty fast there, over a meter a second. Some of these actuators, depending on what you need there. Now we also have a shake table. The shake table has the same purpose here, except it's a shake table. Here's an image before we had anything on the table, really. There's an isolation bearing about to be put here, but this was an experiment that was looking at isolation of equipment. The multi-direction G2 actuators here and one here allows us to control in-plane motion, including torsion and translation. Here is a drone actually right here that took off from here that's actually filming the multi-directional motion. So we have done visualization with some of our experiments as well. It has a pretty good payload. It's something Dr. Cal designed. We didn't buy it. We actually built it, and payload's about 13 kips, about 6 tons at 1G, 6 by 6. That's what, about 2 meters by 2 meters almost. And the stroke is 7 and 10 inches in 2 directions with peak velocities of 51 and 29 inches a second. So it can meet quite a bit of demand. So here's the directions here that we can accommodate. You say, can we go vertical? My answer is not yet, but that's in the plan to go vertical. So it's going to be 6 degrees of freedom. You've already heard about this, the debris, tsunami debris. We have high resolution, high bandwidth load cells. Other equipment, the soil box. This is the one I showed you earlier, 6 by 6 by 6 width, dimensions, and height. You can actually stack 2 of them. Has advanced instrumentation. You can really get some high quality data. Professor Suleiman, whose name will come up here shortly, is the overseer of that. Here's Professor Suleiman's name. We have also now, this is the big sister soil box here. You see it for scale here. This allows us to do very large scale soil testing here, and has advanced sensors again with electric actuators, multi-direction. We can handle 6 degrees of freedom at the top of, say, this pile that's there. Also, we have a control room right here that allows us to do hybrid simulation with anything in that soil box. Back here is a shake table. Here's the furnace, by the way. I don't know if you can see my cursor. Up here is that mezzanine with some of the other test beds I referred to earlier. This offshore wind testing facility is really part, or should I say the soil box is a part of that. Again, Professor Mohammed Suleiman is the overseer of that. I'm not serving it justice by naming it by its official name, so we have to forgive me, Professor Suleiman, but it does have an official name, but it's really the Offshore Wind Turbine Testing Facility at Lehigh. And we've done hybrid simulation. This shows, and this has been published, earthquake and engineering structures, and some other papers are out coming. You can take a look at those. Just Google either my last name or Professor Suleiman's, or it's in engineering structures. Now, fire, here's our furnace. It's reconfigurable. So it could handle, and it could be built around structural components that could then be tested, say, as part of a hybrid simulation. So with that, I'm going to pass the torch here to the next speaker here. So Joe, I think you're moderating there. Or... I think, hang on a minute here, I'll go ahead and moderate here. So Liang, you're going to be up next. I'll let you take over then. So Liang, Dr. Liang Cao is our research scientist. Liang, you hear me okay? Can anyone hear me?
Jim, I can hear you.
Oh, okay. I thought maybe the internet may have broke. Okay, sorry, Joe. I was just introducing Liang. Okay, thumbs up, great. Okay, well, Liang, I'm gonna pass it on to you there. Liang, are you there?
Okay, we can go out of order here.
If you wanna, yeah, when we do that, we can come back. If
Okay.
not, I can do Liang's presentation. He may have been, internet may have broken down. Whatever you want to do, Joe.
Yeah, I'll just walk through my slides here.
Okay.
Give me a second. Okay. Yeah. Can you see, Jim?
Yeah, it looks good.
Perfect. All right. So yeah, sorry about that. We're gonna go out of order here a little bit, but so I'm gonna walk through guidelines for proposal prep. Right. So this is related to when you are either developing your NSF award or a non-NSF award too. You can use the facility even with a non-NSF grant. You know, what are the steps here? How do you interact with us as a facility? How can we help you put your proposal together? And then what sort of questions you want to come prepared with when approaching us, and then what you can expect from us and the questions that we'll likely have for you. So, um, as mentioned, right, we're, there's a few phases of proposal development. There's the pre-proposal stage. That's where you're kind of before you write your proposal, what you need from us during the proposal writing stage, which I'll go into some detail, we help with for sure. And then the post-award stage. So if you're awarded, you know, what are the steps that we have to take in order to schedule and make sure that resources available and et cetera. So, right, the opportunities here for utilizing NHERI Lehigh and then the Greater Atlas facility are both public and private sources, right? So if you are coming to us with an NSF proposal or an NSF grant, you'll be able to utilize NERI Lehigh to the fullest capability. So you'll be able to utilize the NERI Lehigh operations and maintenance budget, and then in addition to your NSF funded research project. If you're coming to us with a non-NSF source, so that could be another federal government agency, public government agency, a state agency, or a private source of funding, then your project would be responsible for all costs associated with the project. So I'm just going to walk through here some of the different steps here. So the first is user proposal preparation. There is a link here to our website that has some additional resources. So, you know, when we upload these slides and this presentation to our website, you'll be able to access these links quickly. So the pre-proposal stage, right? The first thing you'll want to do is, you know, a great first step is sitting in this researcher workshop, right? So you get an idea of, you know, what we can do for you, what our capabilities are, right? And then, you'll also want to go to our website for sure. We have a ton of additional information there. Um, uh, you know, good first steps, aside from this workshop, is reaching out to either myself or Dr. Cow. You know, either one of us are very knowledgeable about the facility, and we are both experimentalists ourselves, so we can certainly help you in many different ways. I have some listed questions here that you might want to consider before approaching us, which is, you know, can our facility facilitate what your testing idea is or your simulation idea is? Do we have the capability to support? And if not, that's not necessarily a problem. We have expanded capabilities over time. to meet researcher needs. So it's still a good first step to know and understand whether or not you can immediately come in and jump in, or if we'd have to work out a way to expand capabilities. It's kind of what I had mentioned there on that second bullet too, equipment and instrumentation. The third is important. What solicitation are you putting together your proposal, and what's the deadline? We've had, unfortunately, people come a few days in advance of them submitting proposals, and it's very difficult for us to give you good quality information in terms of scheduling, budgets, technical ideas, and help with a proposal if you're coming to us on such short notice. So we generally like to have as much notice as possible if you're planning on working with us. Thank you to those who have given us many weeks and months in advance. It's much easier for us to help you really hit a good proposal. And then, any additional information that you think that we'll need in order to help facilitate your proposal. As mentioned, we have a lot of resources on our website. So again, hyperlinks all over here to our website with additional documentation. These are some tips on writing your proposal, and then specific areas like utilizing the facility, which include resources, your research plan, schedule, budget, and then a data management plan, which I'll go into all of those in a bit more detail later. Some other useful resources on our website are our usage rates for both NSF and NHERI projects. So those are projects that you have funded through NSF and you're coming to use the facility. Usage rates for non-NHERI projects, that would be other federal agencies, other state agencies, et cetera. The responsibility of costs. So if you're coming in with an NSF project, what is your responsibility through your NSF grant versus what is our responsibility in terms of the operations and management budget that we are afforded. That data management plan, our lab safety plan, and then a user's guide, which has really a summary of a lot of the information that we're presenting today. So then, what do you need during the proposal writing stage? As mentioned, right, reaching out to us the sooner you can, the better. We really recommend you read through the PAPG, the NSF's PAPG, which is the Proposal and Award Policies and Procedures Guide. That'll give you information on how to prepare your proposal. You'll want to communicate with us. And then again, I'm going to repeat these kind of line items multiple times here, but this is really critical for us as a facility to help you, which is what resources do you need? What sort of timeline do you have in mind? We will certainly help you with a budget, but if you have a budget in mind, giving that to us, and then your data management plan. In more detail, the research plan is a general plan of the scope and what you plan to do here at the facility, and a description of both experimental and simulation methods and procedures that you'd need from us. Facility equipment and other resources. What resources do you need in terms of equipment, instrumentation, and then additionally there's personnel, right? So we have expertise in a number of different places in terms of instrumentation. Dr. Cow has his expertise in hybrid simulations and experimental work. Obviously Dr. Rickles as well. So we have a broad range of capabilities in our staff. So what are you planning on doing? And then we can kind of help you align with who may help you with your project while you're working with us. And then right. So I guess that last bullet here, NHERI Lehigh EF can provide additional information as requested. So right, the dialogue doesn't have to stop at this workshop, right? I really implore you, if you're interested in using our facility, to look at all of this information. It's a lot at once, as Dr. Rickles had mentioned before. There's no expectation for you to remember all of this at once. So that's why we provide a lot of this information on our website and these links. And then if you have an idea and there's anything specific you need additionally, then reaching out is the best way. Our schedule and budget, these are two things that are quite important to me as the operations manager. So making sure that we're keeping all of our projects moving. What we need from you is an idea of when you need certain resources, including equipment, instrumentation, and personnel, like I had mentioned before. And then the budget, of course, that's important to all of us, both us and you. Our goal is to keep things within our budget that you give us, and we want you to have a realistic sense of uh, what you need to budget in order for us to execute your ideas and your research. Um, I had mentioned this before, but right, the breakdown between NSF funded and non-NSF funded projects. There's more details on our website. Additionally, the responsibility of costs has a breakdown of, if you are responsible for your NSF project for budgeting, or if our NHERI operations and management budget will cover costs. So you can always reach out to me if you have additional questions or need information. The data management plan, right? That's really important to NSF. So something that you have to be mindful of when you're working with our facility or any NHERI facility is that at some point at the end of your research, you will need to publish your data that we generate together. So this will need to be uploaded to Design Safe, which is NHERI's repository for data, and that will be published with the DOI. So that information and data needs to be published. So having a data management plan is critical on how you plan to execute that, and what type of data you plan to upload and generate. So all important for an NSF proposal specifically, and using our site with NSF grants. So then, jumping into what it looks like once you have a project here, there's user training, developing the experimental protocols if needed, specimen construction and instrumentation. Then we'd go through testing. We'd upload raw data and then curate that data onto Design Safe as we're closing out. And then we'd need to demolition any of the fixtures or specimens that you have that we've constructed. So some user training documents that we like to use, and really what these are for to make sure that you, when proposing to our site, you'll be able to actually utilize what the resources that we have, right? So there's an equipment, facilities, and policy compliance check that just goes through, what's the experimental feasibility that you're proposing and using our site. Making sure that safety is paramount. That's a very high priority item for us here as an experimental facility. What your budget, schedule, and data look like. If you had come to us already before, during the pre-proposal or during the proposal stage, that makes the post-award stage smooth and seamless, because we will have worked together already on a budget, considering safety, had looked through experimental feasibility and a schedule, right? So again, the earlier you talk to us, the easier it is from pre-proposal all the way through post-award stage. And then a site utilization request form. This can also be in a form of an email, letting us know that you want to use the facility and when you want to use the facility. And again, if you had walked through the proposal and then to post award stage and notify us that you've been awarded, we'll already have a lot of the information that we need in order to start scheduling you. Kind of went through all this already. So I want to jump to researcher training and then some of the other steps during the post award stage. So researcher training, again, is incredibly important to us. Depending on whether or not you'll be utilizing the equipment, you'll need to be trained on how to utilize equipment if you need to. Safety is always, again, paramount to us. So if you are planning on coming to either visit the lab or partake and witness your experiments, you'll need to be safety trained. And then controls and data acquisition, right? Again, if you plan to be hands-on and want to control your experiments, right? You'll need to, you or your students or postdocs will need to be trained on how to utilize our equipment. And then also in terms of data acquisition, installing data acquisition, sensors, strain gauges, whatever you have or whatever we have and you want to utilize, training is important. The experimental test plan and scheduling and testing, right? So that'll be an ongoing dialogue between you and us about, what sort of days, time, months, weeks do you need blocked out in order to perform your tests, and what does that look like, right? What equipment do you need? What personnel do you need? When do you need it by? Details of the entire scope of your project, specimens, where you're fabricating or refabricating. Are you getting an external fabricator? Are we erecting? Are you getting an external erector? All of these details, we'll want to both flesh out and make sure we're have the same understanding so that we know what we need to do in-house in the lab. Then we'd actually go about fabricating or erecting or whatever we need to do, instrumenting, getting your specimens and your experiments set up. And then we'd actually execute the testing, which we'd also need to schedule, right? So we'd first schedule getting everything set up. Then we'd schedule any controls and protocols that we'd need to develop, and then finally execution of the testing itself. And then 3.5, post-test data archiving. I mentioned this before, but this is really important. Again, any NSF grant needs to have that data uploaded onto Design Safe. So it's incredibly important that you come here knowing that at some point that data will be, once your project is over, that data needs to be uploaded to Design Safe. So that's just a general awareness up front, right? That when you're using the facility, that data will need to be published. And that's it. That's all I've got here. So Leon, you're up.
Okay.
And then you'll go here and then we'll take questions.
Okay. So Joe, is my time still 1:10 to 1:45, or I thought you were next to me?
Well, I just jumped in front of you, so
Okay. So
you've got until 1:45.
Okay, gotcha. Thank you. Let me share my screen. Are you able to see my slides?
Yes.
Okay. Okay, welcome everyone. So my name is Liang Kao. I'm a NHERI Lehigh research scientist. Right now I'm gonna go over some our example research projects. Here is the table to show our recent and current projects at NHERI Lehigh. So the highlight one is what I'm going to talk in details, and you can see we have a multiple project from either from Lehigh universities and outside universities, and this project are including different type of structures. Some of them are wood structures, steel structures, reinforced concrete, and some of them are testing non-structural components. So the first one would be the collaboration project between Iowa State and Lehigh, where investigated cymatic control cladding. And second one is large-scale testing, talk about the tall wood buildings. They are discussing a resilient-based seismic design methodologies from Colorado's schools of mines. Third one is collaboration research between Princeton and Lehigh. They are investigating a shared buckling mechanisms for in-house performance of thin plates, and they're utilizing they're doing like quasi-static testings. They're also utilizing our DIC system to capturing the shear deformations. The first one will be the another large-scale testing from the PI is from Robert from University of Arizona. They are investigating the seismic performance on the seismic collectors in steel building structures. Third one is the collaboration research between the University of Illinois and Lehigh's. The PIs Larry and Richards from Lehigh, and they are studying about the frame spine system with force limiting connections for low damage seismic resilient buildings. And we also have a collaboration research with University of Oklahoma on scar harveys, and we study about the seismic floor isolation system utilizing the new multi-directional shake tables. And we also investigate some different type of dampers. One of them is the project is from Southern Methodist Universities. The PIs Dr. Nico Marquis. They are studying the new type of pressurized sand dampers. We also study the real-time hybrid simulations on soil structure foundations using neural network. And then we also had a collaboration project with the Florida International Universities where we utilizing the real-time hybrid simulation to study the wind-induced aerodynamic vibrations. And the last one on this slide is also from is studied the ultra high performance concrete foundation systems, which is also is a collaboration project from Mohammed Suleiman's where we study geotech informations under the offshore wind turbine. Next slide, the first one is we study the self-centered seismic dampers. This utilizing the shape memory alloy. This is a project from University of Virginia. The PI is the Dr. Osmans, and this is our current project. We also had a project from University of Harvard. The PI is Claudia Marine, and they are studying the damage detection and localizations method utilizing the DIC systems. And we also have 3 career awards where the PI was collaborate with us and utilize our testbed, and then they got some preliminary data when they submit to NSF and get recent career award, including Dr. Scott Harvey's University of Oklahoma is studying the seismic risk on these nonlinear 3D isolation systems. And Dr. Austin Downey's University of South Carolina studied on data-driven control of high-rate dynamic systems. And also Barbara Simpson's, she's right now is in Stanford University. When she submitted this proposal, she was in Oregon State. The career proposal is studying the real-time hybrid simulation systems with GPU computers. So we're gonna talk about the details of some selected project. The first one is a collaborative project between Iowa State and Lehigh Universities. Dr. Simon LaFlamme was the PI of this project at Iowa State Universities. The overall is we're trying to improve the performance of buildings for multiple hazards using control variable friction cladding panels. So the idea is we in Iowa State we 3D printing designed semi-active friction connection device utilizing to connect the floor slabs with the claddings, and the scope is designing the cladding connectors and using semi-active control law to mitigate multiple hazards and performs large-scale real-time hybrid simulations to validate the dynamic models we come up with from Iowa State Universities. And at Lehigh, our scope is to design our prototypes buildings and then performs nonlinear time history analysis to assess the connector's performance. Also, this is our both goals is perform large-scale real-time hardware simulations to study the semantic control panels performance. So what we did first, we did real-time hardware simulations utilizing our 40-story tall buildings subject to multi natural hazards. So there, from this graph, you can see the details of analytical substructures. So this is 40-story buildings, including 2 outrigger columns on the north and south base, and on the outrigger columns, we're installing 12 nonlinear viscous dampers to mitigating the natural hazards. And so the experimental substructures will be a nonlinear nonlinear fluid viscous dampers installing on outrigger columns. And the details of the entire 40-story building was modeling as analytical substructures, including the nearly 7,900 degree freedoms and nearly 3,000 elements, including 2,411 nonlinear four-space fiber elements and 11 nonlinear explicit Maxwell elements. So with real-time model updatings. So the reason we are doing that is we have for this prototype buildings, we gotta install 12 dampers in here, but we can only using 1 physical dampers in the lab, and then numerically model the rest 11s as a numerical dampers. However, those numerical dampers will be updating their model parameters using existing physical dampers during this real-time hardware simulation procedures to get more accurate results. And we're also including the 552 nonlinear truss elements. So the entire buildings will be nonlinear structures, and we just utilizing a large scale viscous dampers in the lab as experimental substructures. So before we doing the experimental substructures, we also did a characterization test to build a numerical damper model. So this characterization test is typical test protocol, which can be doing for any type of the damper studies. So this is we're doing a harmonic displacement control test, including 2 ramp-up cycles, 3 ramp-down cycles, and full cycles. And we did the different frequencies, and you can tell the damper force is highly related with velocities. It is rate dependence. So that's also highlights the reason we have to do the real-time hardware simulation. We cannot slow the test because if the damper force is related with the speed. So this is the videos of 3D real-time hardware simulation and the earthquake. The earthquakes was scaling to MC levels, and you can see the top graph is the top views of the roof displacement from north and south directions. The middle 2 graph is a 4-story north-south and east-west BRB frame, and the bottom graph is the damper performance. You can see the BRB frame have a highly nonlinear behaviors under the earthquakes, and also the nonlinear viscous dampers installed on the top 40 stories dissipates a lot of energies based on this dynamic force displacement plot in here. Instead, we also studied the wind load. So this wind load is actually capturing from the FIU facilities, also one of the NHERI experimental facilities. In there, we build a aerodynamic model, which is in their lab, and you see this is a 1/150 scales to mimic these 40-story buildings, and we including 338 prototype on this building all around all surrounding on the surface. So we are able to capture the 3D wind load, and we are using this 3D wind load to study as external excitations. And instead of that, because those nonlinear viscous dampers is only installed on outrigger columns, which is can only only have a major effect on the north-south direction, but on the east-west directions, those outrigger columns will not providing that much effect to mitigate the wind. So instead, we also adding two mass friction dampers on the top, which is as also as another experimental substructures. So this is the video. So the two mass dampers we're using is what we developed before, what we call rotary friction damper. Is also one type of semi-active friction dampers. But for this wind studies, we are only using this friction damper as its passive mode, where the friction force will become constant. So this is the same graph. Instead of we are also adding the numerical friction dampers, the two mass friction dampers on the third graph, and you can see under the wind load, this is pretty much first frequencies dominant. Is the difference then. So also the wind is blowing in 45 degrees. So that's why you can see the top floor is the wind is blowing on the 45 degrees, and also we have a lot of vortex shedding effects to generate this shaking things. So this is also why we have to do 3D hybrid simulations, because if we only model in the wind in one direction, we're not able to capturing the vortex effect. And you can see the under wind load, the BRB perform linearly. This is as what we expect. Also these two dampers, one is the friction damper, one is the viscous damper. You can see their energy dissipation is quite different. So this is another highlight is we're not only able to do hybrid simulation using one experimental substructure, we can also do different type of experimental substructures in utilizing their 3D real-time hybrid simulations. And here's the results. This is just brief overview. So after we installed nonlinear viscous dampers in outrigger columns, we are able to reduce the earthquake by maximum story drift by 22% reductions and 25% reductions on the maximum accelerations. Under wind, we are able to do 35% up to 35% acceleration reductions, which is pretty impressive. And also, this is a project between the FIU, Florida International Universities, and Lehigh Universities. Instead, what we just seen before is we had a same 40-story building, and the wind load was pre-record using aerodynamic model. What this means is aerodynamic means we're building the model prototype, and it's a fixed space on the wind tunnels. Instead, in here we try to study the air elastic effect, where we develop a new type of technique called 3D real-time air elastic hybrid simulations. And instead, what we can do is instead of only have experimental substructures and analytical substructures, we also adding something called air elastic substructures, where this air elastic substructures is built in the FIU wind tunnel to capture real-time wind force. And those air elastic substructures have a rotational centers underneath. And we are utilizing two electric actuators where the substructures can move in real time based on the simulation coordinators. So basically, this air elastic substructures can capturing the real-time wind force under certain deformations of structures. And also we can also adding some physical dampers to the building, and then using the experimental substructures where these dampers can also be controlled by electrical actuators in here. So this is the videos when we are doing the 3D real-time area elastic hyper simulations on the building itself without the dampers. And in this study, first we modeling the buildings as a linear model, which is only modeled at 2-degree freedom systems, and we speed up the test. We speed up the videos because the real test will gonna be really long time, like about 10 minutes. So we don't want to you look at the 10-minute videos. And the most important part is you can see the wind is blowing on its short east-west direction, but the most vibrations is coming from the southwest directions, which is this vibrations is actually caused by the vortex sheddings. But this is also the important things is under wind load, we have to modeling the structure in 3D. Otherwise, we are not able to capturing this vortex shedding effect. And here's a quick results comparing the area elastic model with aerodynamic models, where aerodynamic model means you have a fixed based models built in the wind tunnel. You can see these we are showing here is called the mean CP values, which is indicates the wind pressures are distributed on the surface, especially on the west surface, which is windward directions. You can see there is up to 40% change in the mean CP values, considered area elastic effect, which is really important because it can also related with your wind design procedures. If we are underestimate the wind force by 40%, you're probably gonna change a lot on your design. So instead of the that, we also studied the soil structure foundation interactions using the neural network. So the difference between the challenge on the studied soil foundation structure interaction is how you're going to modeling the soil. In traditional way, what if you modeling soil in the open seas, it could including thousands and thousands degree freedoms, which gotta be impossible to do in the real time. So in this case, we are studied utilizing the neural networks to modeling the soil. So the structures is remaining the same. In these studies, we are doing the same 40-story buildings, but modeling the buildings in 2Ds. Instead of the soil, we are using 4-layer neural network models. There's 8 inputs and 8 outputs, which can significantly reduce the comparing with the conventional finite modeling 1,000-degree freedoms, significantly reduce the computation times. We also comparing the results of the soil using OpenSys models. You can see they are matched very well. And by studying the soil structure foundation interactions, when we studied the real-time estimations, including the soil structures interactions, we're comparing the results with and without the soil effect. You can see there has a 50% change on the roof displacements, which is also a significant change, which has highlighted the soil structures also potential studies in the futures, which because none of the structures are sitting in a solid concrete floor. They are standing on soil, and the soil will gonna play a very important role in the future's natural hazard study. So this project is a collaboration project. It's a not collaboration project. It's a project from University of Oklahoma, from Dr. Scott Harvey, which investigating the multi-directional nonlinear dynamics of floor isolating systems. Our NHERI Lehigh facilities, we are acting as a test facilities. We providing test bed for their studies. So this is when you consider when you're writing proposals, we don't have to be the co-PI, so we can also be a user serving centers to provide you the results. This is what we are doing for Scott Harvey at University of Oklahoma. So basically the scope is we are try to perform large-scale fluor isolators structures characterization test to experimentally validate this physical-based mathematical model. So first, we install the fluor isolator systems on our shake tables, and we run characterization tests, and then providing data with them, they can do numerically model these fluor isolation systems. And we also perform large-scale real-time hybrid simulations to quantify the performance of these fluor isolation systems into different type of buildings. And you can see the fluor isolated systems is actually standing there. The red beam is trying to mimic the non-structural component weight, because this fluor isolator systems is not for structure, it's for protecting the non-structural components, such as like heavy expensive equipments in hospitals. They can standing in top of these fluor isolator systems. There's a 3 restrainers is capturing the resistant force from the fluor isolator systems. First, when we did the hybrid characterization test, we find out this fluor isolator system is highly rate dependent. You can see when we applying different at different speed, the shear force the restoring force we capturing from the fluor isolator system are quite different. So when with increasing the velocities, the high frequencies have a really significant effect on the response. So here's that's the reason why we have to do the real-time hybrid simulations. In here, so the real-time hybrid simulations, what we did for this study is we create not only the 3D buildings, we also modeling the coordinates in the structures, where the coordinates and the buildings are both the analytical substructures, and the experimental substructures is only the isolator systems, which is connecting this coordinate model with the buildings. And once the excitations, the simulation coordinators receive the input excitations, we give command on both analytical commands on the buildings and the experimental command on the structure on the fluor isolators, and we got a restoring force feedback from both experimental substructures and analytic substructures. So here, this is the videos of these studies. The top 3 graph, the top left 2 graph is the normalized restoring force of this fluor isolator system in 2 directions, and also the top views of these fluor isolator systems. And the right bottom graph is the 3D views of these fluor isolator systems. And you can see these the results are quite different in 2 directions, because once the fluor isolator systems have some very significant divot effect when the isolators reach in the middles, because typically these fluor isolator systems are the heavy beam are sitting on a ball bearing, and then this ball bearing create a divot on the plate. So that's how it causes like jumping when the fluor isolator systems reach to the middle point. So here's the quick results. By using these fluor isolator systems, we're able to have reductions on this equipment, reductions of the equipment accelerations about up to 80% in one direction, and the other direction is 70%, which is pretty impressive. The next project is we investigate a novel pressurized sand dampers utilizing our cyber-physical test dynamic lab test beds. So in here, we just studied the damper performance. So first, we studied the scope of is to characterize to conduct the characterization test to study the dynamic behaviors under different temperatures. This is what we did. We are building using the wire type heaters to heat the damper. This is damper mock-up. When we are doing this, we have a different type of thermocouples to test the damper to test the heater performance. And then we also did the heating test on these dampers to by conducting the polarization test. And also we also performed the real-time hybrid simulations to validate its seismic mitigation performance. So typically this dampers is utilizing the sand. There's a piston rod in the middle with some spheres to generate the pressures on the sand, and also the total damper force is coming from the pressurized sand with the frictions, and we're using a 4 nuts to give a pretensions on the steel rod in the corners, where we can give a pre-pressures on the sand. So there's quite a difference than the typical friction dampers. Typical friction dampers, we will have constant friction force because right now we have a pressurized sand. When the spheres reach to the end and the sand have nowhere to go, so we generate high pressures. That's why you can see this pinching effect. So to study, to do the hybrid simulations, here we are investigate the performance of this sand damper by install these sand dampers in a CLT rocking wall, because we know the CLT rocking wall, including the post tensions, it has self-centering capabilities, but in typically lack of energy dissipations. When we're adding these dampers on two sides, we are hoping this damper can enhance the energy dissipations of this self-centering rocking walls. So in this case, the self-centering rocking wall was modeled as analytical substructures, which is we are utilizing a lot of like nonlinear elements to mimic the rocking effect. And then we have two experimental physical dampers, pressurized sand dampers on two sides to study its performance. So this is the video of this test. You can see the analytical substructure rocking wall as analytical substructures is rocking. You see the gaps open and close during the seismic performance studies. And the bottom one is the base shear with a story drift. You can see the self-centering capabilities. And the left two graph is the energy dissipation from these two sand dampers. And you can see it have significantly energy dissipations, which can also be shown in this base shear and story drift plot. If there's no dampers, this will be a straight line. And we're comparing this hybrid test with the elastic wall, and you can see there's a significant reductions on this base shear and roof accelerations. So this the last two project, which is the large scale testings. So this one is a collaboration research project between the Colorado School of Mines and the Lehigh universities. In here, we are designing and the overview is try to design, construct low damage resilient 3D CLT buildings and investigate the lateral load response and damage of the self-centering CLT walls and their multi-direction loadings. So we built this it's a 5/8 scales CLT wall, self-centered CLT rocking walls in our lab, including the floor and then the columns. And we are trying to do a multi-directional loading test to study its performance. So here is the technical details between the collector beams to self-centering wall and the floor diaphragm to self-centering wall as well. So the test we did the test was sub-assemblies, and we designed the considering force and deformation demands expected during the multi-directional lateral load testings, and 3% story drift as performance object for damage initiated to sub-assembly components and connection details. And in here, we also develop a multi-directional displacement control themes because this the actuators we're utilizing 4 actuators, large-scale actuators to driving these large-scale test placements on multi-directions, and those connection point on the actuators is not the control point. The control point is the centers of these floor diaphragms. So that's why we have to develop displacement control schemes to controlling the implant on outflow plant floor drift and vertical motions. And And all this connected kinematic relationship between the control node, feedback displacement sensors, and actual command displacement can be found on the Alia's dissertations. She was the PhD student studied this project. And here is the videos when we are doing the quasi-static multi-directional testings. And the target is try to hit the 3% drift in both directions. You can see this in-plane and out-of-plane motions. And the left right bottom graph is the in-plane low drift with the out-of-plane low drift. So we speed up this video. This is actually quasi-static testings, and you can see the self-centered capabilities where. And the last project is the recent one we are doing in our lab. It's also current ongoing one is to study the performance of seismic collectors in steel building structures. This is a collaboration project between University of Arizona and Lehigh's. The project overview is investigate failure critic components of steel seismic force resistance systems, which is seismic collectors, to do finite element analysis, large-scale testings. The most important part is in here, we are using 4 large-scale hydraulic actuators to conducting the up to 1,000 kilonewtons axial force. So in our lab, the project will be used to support to supporting the finite element modelings and studies of collectors and floor diaphragms. So you can see the graph. This is a huge, really large scale testings. This test was done on May 7th on this year's, and where we're conducting around like 2 million pounds, 2 million newtons force on these seismic collectors. So here is all the projects. Thank you very much. So I'll get back to you, Jim.
Yeah, thank you, Liang. I guess we have about 15 minutes, so we're right on schedule here for any wrap up. I guess first, does anyone have any questions? I don't think they're allowed to talk, although I have the override. Maybe if you want to raise your hand, if you want to perhaps type your question if you haven't done already, we could address any questions that way. We could see how that works. Any questions from anybody? It doesn't look like you guys are kind of quiet, so no exam, so there's no questions there. Usually if there's an exam, people ask questions. Okay, so well, hopefully what you heard was informative. We've give you a little bit of history here. We've been a facility like this. We started at Atlas in 1987. And the Atlas facilities existed there, and that is complemented by the NHERI facility, which originated actually in 2002. That was during the construction phase. So we've got a lot of things that, we welcome you to come visit us and see. Our next workshop actually be in person. There will be announcements that will be posted here, so you should keep an eye out for that. And the objective is to have people write proposals to NSF. If you use the facility and you have an NSF grant, essentially the cost is minimal. The major cost would be for your specimen. That's the majority where the cost would be. Maybe if you had some very special fixtures, but typically we can cover a lot of that. So it's very, very economical to consider using a facility, and the NSF is of course sponsoring us, so they endorse that. And if you have an NSF proposal and you didn't think of using facility, any NSF grant can use a facility, so you should exploit that opportunity because it exists, but also NSF actually likes the idea of people using the facility since they are supporting it. So I think what we should do there, since there's no questions, we can go ahead and adjourn here. And I want to thank you for attending the